Ladies and gentlemen, please take your seat for the most exciting show of the last 100 years. Einstein presents the Great Relativity Show.
Light always travels at a constant speed.
And here's the man you've been waiting for, Mr. Albert Einstein. Oh, and don't forget his glamorous assistant, Mimi.
Oh, please. No, thank you.
Now, Albert, I want to know about the special theory of relativity. I want to know what it has done for us.
Well, the satellite navigation system used to land your airplane or get you home in your minicab are all based upon my original theories.
To understand these theories, we must first look at the behavior of light.
Right. Now, what's the first thing we have to know?
That light always travels at a constant speed.
Well, I have heard that before, but what does it mean?
Let's look at the motion of a speeding bullet.
Take that, you fiend!
The bullet travels at 500 miles per hour relative to the ground. But if the gun is shot by someone in a moving car, the bullet's speed relative to the ground will change. If the car travels at 50 miles per hour in the same direction as the bullet, then the bullet will now be going at 550 miles per hour. It's simple, yeah?
Simple indeed, but so simple that everyone assumed that light also behaved like the bullet. Only in the 1860s did James Maxwell, a scientist from Scotland, theorize that light might be different, that it would always travel at the same speed.
In other words, if someone shines a torch instead of a gun,
Take that, you fiend!
the fact that they were driving a car or standing still on the road makes no difference. The light's speed will always stay the same. Einstein was the first to take Maxwell's idea seriously. He imagined what it was like to ride a beam of light.
Faster, damn it. Why does he not go faster?
Einstein knew that all of our experience of motion is relative. You cannot detect motion inside a space without reference to an outside point.
When the blind is down, they think they are stationary. Only when they look outside do they realize they are moving. I deduced that if the speed of light varied, then as your vehicle sped up, the light within it would change. You wouldn't have to look outside to see that you were moving. This was too ugly to imagine.
So now we know. Light will always travel at the same speed. This has since been measured at 186,000 miles per second.
Time is not absolute.
To understand this, we have to know that the speed of light is constant. It travels at 186,000 miles per second, and it's the fastest thing we know.
Tonight, we're going to show you how this affects time and space.
So, the speed of light is measured in miles per second, in the same way that we measure the speed of a car in miles per hour. Well, how far have we gone?
50 miles, and it only took an hour.
Well, I think we got away.
So the speed is 50 miles divided by 1 hour. Or speed equals distance divided by time. We know that in the case of light, speed cannot change, and therefore time or distance must.
But I hear you say, a second is a second is a second, measured by a great big clock in the sky.
What Einstein saw, and it nearly gave him a nervous breakdown to see it, was that our experience of time is variable.
No. There is no clock in the sky.
He claimed that moving clocks run slow.
In fact, this has since been proved. Have a look at this.
2 twin air hostesses. They have perfectly synchronized watches. One is on a plane, the other is in the terminal. The plane lifts off and circles the world. Arriving back, the clocks show a different time. One twin is a fraction younger than the other.
And when we talk about the distances involved in space travel, this makes a real difference.
But how do we explain this? It goes against all our everyday knowledge. Well, let's go back a minute.
We know that in the case of light, speed cannot change, and therefore time or distance must.
It all depends who measures it. Oh, look, the love train's coming.
Oh, darling, that was wonderful.
Yes, the earth moved.
Yes, it did. Let me see your face.
The light traveled up from the torch, hit the ceiling mirror, and reflected onto her lover's face. The watch on her slender wrist measured a tiny but certain amount of time for that to happen.
But if I'm on the embankment, then I see something different. I see the light moving inside a moving carriage.
Thus, from the bank, the light beam appears to travel a further distance, and therefore from Mimi's perspective, it takes longer to complete its journey to the man's face.
And so time on the train is longer than time on the bank.
Thus proving that time is relative.
Mass and energy are different forms of the same thing.
Now it's time for the most famous equation on Earth. E equals mc squared.
We've all heard of that, but what does it mean?
Well, I put forward the idea that light is the fastest thing in our universe. Nothing can go faster.
But what happens when something else approaches that speed? To move an object, you have to apply a force. How large a force depends on the weight or mass of the object. How much work you do depends on how much force you exert over what distance.
But say you want to get to the speed of light. You move your legs manically, you flap your wings as hard as they will go, you put your foot down to the floor, you reach amazing speeds. But nothing can go faster than light.
So what happens as you get near it?
Oh man, I think we're going to explode.
No, what happens is that the force and work you put into going faster no longer turns into acceleration. Now it becomes mass. You get heavier and heavier, so you need more and more work to go faster. You will never reach the speed of light.
Don't tell us what we can and can't do. Here in America, we value freedom, and if we choose to go to the speed of light, then by golly, we will.
I know it's complicated, but I can show you some equations.
Energy is an amazing thing. It cannot be destroyed, but can only change its form. Take this car. When it comes to an abrupt halt, most of its moving energy will change into heat and sound energy.
But it will also retain a huge amount of energy as mass. That's its potential energy.
Einstein realized that there was a way to measure this potential energy.
To be precise, the energy of an object equals its mass multiplied by the speed of light squared.
So this equation shows energy, which you have when moving, and stationary mass, which you have when standing still, to be two sides of the same coin.
I'd like you to weigh a rubber band, then use energy to stretch it. Okay, now weigh it again and it'll weigh just a little bit more. The energy that you have put in has been converted into mass.
Look at it from the other way. The sun gives out an enormous amount of energy by converting its own mass. Every day the sun shines, it weighs a little less.
In fact, it loses 4,200 million kilograms per second.
What?
Don't worry, it is so huge it will take 5 billion years to burn out.
Whew, thank goodness. So mass is energy waiting to be liberated, if you can find a way to liberate it.
Gravity and acceleration are equivalent.
This idea was first written in Einstein's special relativity theory, published 100 years ago. It had huge implications for our understanding of the world. Time and space would be forever interlinked.
But something wasn't taken into account in the special relativity theory.
And that was acceleration.
In 1915, Einstein wrote another paper that expanded the special into the general theory of relativity. This was the beginning of cosmology as we know it.
He thought about acceleration long and hard. In a moment of inspiration, he realized that acceleration was actually the same as gravity.
It was the happiest thought of my life.
But what does this mean?
Einstein imagined what it was like to fall from a roof, to really feel the force of gravity.
As you fall, getting faster and faster, you feel weightless. A skydiver knows this well. But even when you drive too fast over a bump in the road and fall back to the tarmac, you experience this feeling. Being weightless means that you feel no gravity. It feels like this force is no longer acting upon you.
Now imagine you are blindfolded and by accident fall over. A force pulls you to the floor and pins you to the ground. You think that it's gravity pulling you down, but maybe something else has happened.
Maybe the room has lifted up and is accelerating through space. You would have no idea whether gravity or upwards acceleration was the cause of your fall.
So in this theoretical situation, these forces feel the same, so maybe they are the same.
Seeing gravity as acceleration allowed Einstein to work out equations that describe not only falling lifts, but also the motion of stars and planets and galaxies.
And remember, this was a time before spaceships and astronauts. In 1915, we didn't even know galaxies existed.
He theorized that space is four-dimensional and curved, and that light reacts to gravity, bending around stars, as if it too has a mass.
Now this extends into complex concepts of black holes and wormholes and quasars and pulsars and big bangs and dark matter and crazy things like that.
But Einstein's understanding of the forces around us have had a profound effect on our daily life. Without his actual equations, we would be unable to use the satellite systems that land our planes, transmit international phone calls, or navigate our boats. His theories have also allowed us to understand how the universe began.
And that is pretty much it, folks. All that remains for me is to say thank you so much, and good night.